Neutrons. How do they even work? We conjecture ahead.
Although this is going to be weird, and it's going to be about a different.
Title of the conference was something like Ground Truth or Turtles All the Way Down. And so it seems as though there's one Ruliad. I don't think it rules them all. And it might be just hyper-rulial turtles all the way down.
Yes, it's on the back of an infinite number of hyper-rulial turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
Hey guys, what's going on? Memes here. TGIF, my friends. TGIF. We gotta sleep and still got other things to do. But what's going on here on this Friday evening? Yeah, I basically just used the Scientific American article for the cool picture, so I could use it as a primary background. We should give links and credit where credit is due. I'm just saying. But neutrons. What the heck's going on? So as we spoke about protons the other day, technically a proton is two up quarks and a down quark, to the best of our knowledge and conjecturation. What is a neutron? It's one up and two down quarks. And apparently it decays into a proton, an electron, and an antineutrino. That's pretty interesting. But, alright, where are we right now? The neutron is a subatomic particle, symbol, N, or N raised to the 0, which has a neutral, not positive or negative charge, and a mass slightly greater. It's like 939 megaelectron volts or something. Protons and neutrons constitute the nuclei of atoms. Since protons and neutrons behave similarly within the nucleus, and each has a mass approximately 1 atomic mass unit. That's a Dalton, at least on Wolfram Alpha. They are both referred to as nucleons. Yes, as we pop up there. Their properties and interactions described by nuclear physics. Protons and neutrons are not elementary particles, each is composed of 3 quarks, we think. There was some speculation. Maybe it's a pentaquark, or what's going on here? Again, I think 2023 is going to be the year to see, my friends. So, LDG, what's going on, LDG? Whitechapel, welcome, my friend. Yes, it's. I've not seen your feet. I don't know if you have an OnlyFans, but that's another story. I like feet. But all right, how do we geometrically calculate the mass of a neutron? All right. We go over here. What is this monstrosity here? Our friend Wolfram Alpha. Again, links are doobly-doo. But what we got over here? All right. Actually, no. Here's the thing. We'll go back to our screenshot. Again, laziness. But it's got the equation right there. I hit the thing again! This is why we're so bad. All right. The correct window. All right. What is this equation here? Okay, let's embiggen it. All right, we're embiggened. All right, we can see here, this is the joining map, according to Thad's work in 44. All right, so in order to calculate the mass of the neutron, we subtract the mass of the electron, which we did a couple of videos ago. Excuse me, mass of a proton. Wow, I'm so bad. Subtract that out, and then you divide it by the mass of an electron. Okay, and we set that action equal to 1/3. Oh, these thirds seem to keep coming up. And then we multiply this, and again, this is the primary action right here. Multiply it by mu, in this case representing Soldner's constant, or we'll get to that in a second, plus 3 plus pi. Okay, so got a primary action here. And then to close out, we get the terminal action again. Same one that we're using for most all these things here. It's 1 plus or minus, in this case it's plus 2/3. Huh. 2/3. It's very interesting. If only there was something within these nucleons that had something to do with 3, like 1/3, 2/3. Maybe we can gain some hints. I'm just saying. And then, like with the proton, Euler's number, it's about 2.1 or 2.72, very close to the CMB in Kelvin. I'm just saying. But and again, raised to 3 times the Euler-Maccheroni constant. That's kind of just like the proton. And then times our break and scale symmetry, which happens to be Planck mass times the Planck length over the Planck charge squared, which coincidentally comes out to 10 raised to the -7. It's very interesting. That seems to be around a hinge point where some of our observations and some of the numbers we have start to get a little... It's interesting. But okay, we close that out and we go back to our friend Wolfram Alpha here. Take a look at what the heck this is. When we actually plug in the numbers, okay, so we're solving for x, basically the mass of the neutron. It's our unknown, or what we're trying to calculate for. So we subtract out the mass of the proton. That's what happens when you put it in like this. And then you divide by the mass of the electron. Again, got those things in the previous couple of videos. And we set it equal to exactly what we had there. 1/3 times mu, aka Solder's constant, which is, what's that? Oh, the Ramanujan-Solder constant. In mathematics, the Ramanujan-Solder constant, also called the Solder constant, is a mathematical constant described as a unique positive zero of the logarithmic interval function. Logs are important. It is named after, Srivatsa Ramanujan and George von Soldner. Oh my god, I apologize. I butchered your names. So we got this value here. Oh. Again, happens to be the unique zero on the logarithmic integral function. Again. So we get that plus 3, and then plus pi. Closing action is 1, in this case plus. 2/3 times Euler's number raised to 3 times the Euler-Maccheroni constant. And then since we got 10 to the -7, we basically just divide it by 10 to the 7th. Comes out with this. What's our x? Oh, our x is approximately 1.6749274980229. Oh. According to NIST, physics.nist.gov, the mass of the neutron is approximately, its concise form, 1.67492749804. 95 for the last 2 digits as our bars of error. Times 10 to the -27 kilograms. Huh. Looks a little familiar. Digits 9802, 9804. And the error bars are 95 during the last 2 digits. So, my friends, looks like a geometric derivation of the mass of the neutron. Now again, it just within our realm of persistence, if this is correct, if the neutron is essentially the split, no, it's actually the joining map, isn't it? Yes. So if things are coming together, occasionally there's a little bit of pressure. Maybe they go. Now I'm unsure as a dude on the internet if that's a technical term for it. Might that be why neutrons decay? Might it help if, I don't know, we actually change charge to what it actually is rather than just being, it's just a change of the sign. Nothing's gonna happen or anything. Ben, you took a good shot at it. In a 50-50. I don't know. All I know is if I was flying a kite and I got shocked or something, I would view that probably as a negative occurrence. I don't know. But that's all I got from right now. Oh my god. Whitechapel actually did a video on turtle. I'm gonna say turtle geometry, but there's actually a book on that. I looked it up. I'm like, oh my god, it's kind of nuts. But yeah, someone else had the good idea as well. But there is a video somewhere there. If you just search turtle, I think something. You're gonna get a lot of things if it's turtle. I apologize. Yeah, but that's all we got for now. So hey, peace out, everybody. Be safe. Take care of yourselves. I got a lot of hope for what's going to be happening in the very near future. Peace out, everybody.
Have you guys checked out the Memes of Destruction's channel? He's an interesting dude. I like him.